How does BIM transform prefabricated modular construction from design to construction? At the CIB W78 and buildingSMART joint conference in Marrakech, I presented the benefits and the challenges of incorporating BIM in real-world projects. In this video, watch my full presentation on how BIM impacts efficiency, quality, and coordination. Let's get into the details just like we model them in BIM. Bonjour à tous. Good afternoon, everybody. My name is Daiwa House. I'm a BIM coordinator at Daiwa House Modular Europe, and today I'll be presenting some interesting findings that I have made along with two colleagues, Joeri Davelaar and Terpstra, while implementing BIM, Building Information Modeling Workflows in Prefabricated Modular Construction Projects, PFMC for short. So, offsite prefabrication and modular construction is gaining a lot of popularity due to 6 key benefits that prefabricated modular construction has over traditional conventional construction practices. These are rapid advancement in fabrication technology, so I will be actually showing some really cool examples of how we're using this in our factory. Next is increased material, energy, labor, and cost efficiency. And this is something that is going to also play a role with a decreased environmental footprint because of these increased efficiencies. Now, because it's all done in a controlled environment, this also allows us to increase our productivity while also reducing production times. With this controlled environment also comes safer workplaces. And as last, there's also a guaranteed quality and high consistency. So moving forward, these 6 benefits, when they are combined with BIM, they can be amplified to a higher level. So currently in the field of BIM implementation in prefabricated modular construction, there have been many synergistic benefit studies. The first one, Eric Poirier, who's actually at the conference today, has seen that there is increased labor productivity. The next one is, of course, more precise material specification. There's also better communication and coordination among stakeholders. And BIM can actually help overcome some challenges that hinder the implementation of prefabricated modular construction in construction projects. With these kind of hurdles, such as detailed scheduling or detailed production planning, with BIM, we can overcome that. Now, there are some contradictory findings. These include that some studies find that actually BIM allows us to increase the scale and the quality of projects while minimizing the modeling time, while other studies show that actually developing projects in BIM with Revit is slower than in a 2D workflow with AutoCAD. There are some existing research gaps. Aband et al. Finds that there is too much focus on the qualitative. There's not enough focus on the quantitative results and impacts of implementing building information modeling workflows into prefabricated modular construction. Zhang et al. Does an overview of the literature on BIM in PFMC and finds that there's a lack of information exchange and interoperability among BIM software in PFMC projects, as well as integration of BIM and innovative technologies for prefab construction. Now, another thing that is a little bit more general is that a lot of studies tend to focus on the manufacturing, on one phase. They need to focus more on the larger picture and the later phases of different projects. We have to look at things beyond the manufacturing, but also things that are not just done in isolation. So we need to see how these results come from actual building projects in the real world. So what is the contribution of our study? Well, we hope to have not only the qualitative, but also the quantitative impacts shown in our study, examining how the design, the fabrication, the manufacturing, and the construction look like at our modular housing factory. These findings can help researchers and housing fabricators expand open BIM implementation beyond a single construction phase. Daiwa House Modular Europe, we fall under Daiwa House Group, which is one of the biggest builders and developers in the world. Daiwa House Modular Europe specifically operates in Europe, and we have offices in the Netherlands, Belgium, Germany, and the UK. We work on many various projects, from smaller residential projects to mixed-use projects, and we produce about 4,600 modules every year. We did a little study, and we found that compared to buildings that were built with traditional means in the Netherlands, our modular buildings actually embody only 50% of the carbon footprint. And this is because our designs are designed so that they can come back to the factory, be refurbished, and brought back. You might say it costs more material, but at the end of the day, you're reusing it not just once, not just twice, not just 3 times, maybe 4, maybe 5 times. Excuse me, I'm recovering from a little cold. I went skydiving and it was a little bit cold. Going over to the openBIM workflows and the methodology. We of course use Revit as the main modeling tool with IFCs, not only to collaborate and coordinate among different stakeholders and external parties, but we also use BIM to operate our robots in the manufacturing phases. So we want to use this not only for one aspect of our process, but for many. We used an iterative process, meaning that we chose to replace the 2D workflows step by step by taking chunks and iterating and experimenting with BIM workflows. So we phased out some of the 2D with BIM workflows until we managed to get a more holistic view of the project processes. With our concept design, we start to make the building massings with conceptual model masses in Revit. And these 3D conceptual masses have embodied 2D floor plans, so these already allow for not only geometric information to be shown, but we also have preliminary building information such as dwelling type itemization, floor areas. We also have material and cost estimates embodied in this. So we can start using the model from a very early phase to not only help steer the design, but to also look at how it's addressing the client's needs and how we can improve our process at the beginning instead of the end. In our spatial coordination phase, we take scripts in Dynamo that will replace these basic conceptual module masses with production module models with holes, with studs, and all of the plating that is needed in order to go fully into production and use it with our robotized manufacturing. Moving on to the technical design stage, we use a lot of Revit assemblies to create not only detailed models, but shop drawings for manufacturing. And we use AutoCAD timber framing. It's a plugin that we use in order to take Revit basic geometry, such as walls and roofs, and then within a few clicks of a button after the configurations have been set up, to create fully detailed assemblies with the right modeling and precise detailing work for all of our walls. This also creates detailed shop drawings and nailing lines, junction box locations, which will be then used in our manufacturing process. IFC models are not only used to carry out coordination checks, but they are also inputs for our Dynamo scripts to automate some of the modeling work. In this example, a subcontractor has sent us an IFC model of floor openings that they have modeled in another software. The interoperable IFC file format allows us to import the subcontractor's floor opening model into Revit. Then, a Dynamo script reads the size and location of these openings and places these voids in the model. Once the location and the sizes of these voids are approved among all parties, we then run another script in order to cut the actual voids in our model. This workflow facilitates communication and collaboration while reducing human modeling time and errors without the use of any proprietary software. Mo, he's one of my coworkers actually sitting here, who's leading the programming. Another really important part of our manufacturing process are the module assembly drawings. These are the pièces de résistance for our assembly in our factory. Module drawings that incorporate overall dimensions with coding and tags, which are used to put together the main elements. Our cages are essentially concrete steel floors with portals and beams that are put together. And then, of course, the fit-outs come in, so it's the prefabricated cassettes for the walls and the ceilings. And as I mentioned before, it's like the IKEA model for our fabrication. We carried out a comparison of time between 3 different methods of creating these 10 module drawings, starting from a developed model that had a complete floor plan, no annotations, no dimensions. We wanted to create essentially a time comparison to see how AutoCAD versus BIM with standard default functions versus BIM with an automated workflow using scripts and tools such as the AutoCAD Smart Views plugin can help us optimize our process. Surprisingly, BIM with default Revit functions ended up actually performing the worst. It took 174 minutes to create only 10 module drawings. AutoCAD, it was a little bit better because you don't have to create all of the steps again for every unique module after you have a good line work made for at least one module. You can copy paste it, change some text, and you're pretty much there. But with BIM and automated Revit, it had a 68% decrease in time compared to Revit with default functions, and 62% decrease in time compared to AutoCAD with normal line work. So for us, this was a real big eye-opener because we could automate all those things like dimensioning, tagging, also cropping down views, placing sheets. This was done within minutes with Revit. Moving on to the manufacturing and construction. In our factory, we have 3 main processes that we analyzed. There's a timber framing robot, which is a semi-automatic process of assembling timber framed elements. There's also a Wortmann steel drilling robot, which bores holes in our steel. And we have a new digitalized factory, which I'll explain in a couple minutes. BIM facilitates the operation of the timber framing robot, steel drilling robot, and the new digitalized factory hall. For the wall construction with the Mobi 1 wood framing machine, essentially we went from a production of 8 walls a day using 16 carpenters making walls with a traditional method, with tables, putting everything together, plating, insulating, putting on the vapor barriers. Another process which we implemented a few years ago with a semi-automated robot actually brought our wall production up to 30 while reducing the amount of people we needed. So our wall production increased by 275% and our labor productivity increased by 757% because we needed less people. This drilling robot that we had, of course, it saved a lot of time just by itself. If you needed to make a marking for a hole and then drill it yourself, it took about 5 minutes to do one hole. With the drilling robot, the data entry for all the hole positions and sizes had to happen manually, which would take about 2 hours per cage type. But by implementing an IFC model transferred over to the NC file format using a cloud-based platform, and then with this converted file from the IFC, we can actually minimize the amount of time needed and error because we don't have to have anybody putting in the information. It is read automatically by the steel drilling robot. And the same thing happened with the timber framing robot. It's also an IFC file which has been translated into an MOB file format so it can be read by the machine. And that is how we are using IFC files in order to automate and drive our robotized manufacturing process. Moving over to the manufacturing in our new digitalized halls. In our conventional halls, what we usually have is we have stations. So every module is being built in one place and you have teams of people moving from one place to the other. Of course, building with their tools, moving their equipment, doing all sorts of things from painting to taping foils. And instead, what we did is we took an AGV, an automated guided vehicle, which ended up actually becoming almost like a conveyor belt where you build the cage and the module on one platform. And instead of you going to the platform, the workers receive the platform at their stations. So these automated guided vehicles move throughout the factory seamlessly while all the workers can leave their tools and become more efficient. So this actually ended up increasing our labor productivity by 60%. Of course, we needed a few more people, but we doubled unit production from 25 modules a week to 50. The new hall is not BIM dependent. However, the integration of BIM with a data exchange and management platform facilitates production planning, extraction of building component schedules, assembly sequences of manufactured elements, task lists for workstations, viewable 3D models and visualizations of assembly order, provides drawing and information needed for assembly, and element tracing using QR codes. In terms of construction, on the construction site, we couple our BIM processes with Ant. It's a production planning software which allows us to essentially show things such as assembly order, placement order, and information from subcontractors by using the data and geometry from IFC files to create a unified coordination model. And you can imagine on the factory floor, this can be very, very important in order to know which elements go where. But on the construction site itself, you can visualize very quickly which units need to go where and at what time. openBIM implementation, our main findings were actually surprising. There were many of the expected benefits that came with this, but we also came across a lot of unexpected disadvantages and challenges that came with implementing openBIM workflows. For the benefits, of course, once you have a developed model, the creation of drawings actually was faster than in 2D workflows or workflows with standard functions by using scripts and, of course, using plugins. Also, when we looked at the non-geometrical data, the updates were instant, and by maintaining one source of truth, there was less human error of inputting data. Next one was an improved coordination and collaboration with external parties. So by using Dynamo scripts, we not only used it to coordinate our files, but we also used it to remove some of the manual modeling that had to be done by our BIM engineers and modelers. Also, the BIM collaboration format facilitated exchange in terms of clashes and other important information, not only internally, but with external parties. And in terms of productivity and quality, of course, by removing some of these steps with automated open BIM processes, we allowed for a higher quality product. We allowed for things to move a little bit smoother. It helped increase our productivity not only in the design phases, but also in the manufacturing with these manufacturing robots. And for the disadvantages, if you have a model that you need to develop quickly, unfortunately in BIM it took way longer than it did in AutoCAD. Especially for geometry, updates and changes and revisions. This proved to be much faster and much easier to do for the standard engineer or modeler in AutoCAD and in BIM. But we noticed that Revit, while it's amazing for interdisciplinary collaboration and coordination, it is not a saw. So if you're trying to cut down a tree, you're not going to be using a Swiss Army knife, you're going to be using a saw. And there are many other tools that are better at creating the production drawings and outputs in order for us to produce our modules. The next one is, of course, limitation of currently available hardware. When you have too much in a detailed production model, the performance drops very quickly, and IFC exports take a long time. Employee hesitancy, going from a 2D workflow to an integrated open BIM workflow in our prefabricated modular construction company really took people aback. It was a lot harder to get people on board once they knew that developing projects in BIM was slower. There's a stigma that was created. So we had to help people understand that, okay, maybe some things like developing the project take a long time, but for later phases like manufacturing, cost estimation, things can actually go a lot faster, and there's more than just one value with BIM. There are many values. While many benefits of BIM are well known, there are many lesser known disadvantages and challenges that must be considered when implementing open BIM workflows into PFMC projects in the construction industry. This study primarily focused on incorporating BIM workflows in PFMC projects at the design, manufacturing, and on-site construction stages, rather than facility management and operation. Future research should analyze not only the qualitative but also the quantitative aspects of open BIM workflows in later PFMC project stages. It should also explore the automotive industry for a balance between product flexibility and standardization. Oh, time is up? I just want to end with one sentence, okay? This is my elevator pitch. The effectiveness of BIM implementation in PFMC to solve built environment issues tomorrow depends on how we implement and develop this technology today. Thank you. If you would like to read the full paper, the link is in the description down below. And if you're interested in BIM and the relationship between food and spatial design, then subscribe to this channel. Thank you to the conference organizers for accepting our paper, and thank you for watching. And remember to savor the flavor.